impact, costing the world 3.5% of its GDP per year. There are human factors as well, with injuries and deaths being caused due to accidents that arise through equipment failure caused by corrosion. And finally, there are the environmental impacts. These range from the less noticeable, with corrosion causing reduced efficiency that leads to greater fuel consumption, to the more extreme, such as the 2006 Alaskan oil spill that saw 267,000 US gallons of oil spilled into the environment due to corroded pipes. In this event, 3 experts in their field shall discuss work to do in combating corrosion and its effects. Professor Mary Ryan of Imperial College London, Professor Richard Jones of the University of Manchester, and Dr. Mark Irwin of Akzo Nobel will provide insights from academic, political policies, and industrial standpoints, respectively. I shall now hand over to our chair for the meeting, Professor Tony Ryan, to introduce the speakers in more detail.
Hi everyone, my name's Tony Ryan. I'm sat in a hotel in Jordan, so proving that we can do these things internationally. As you've heard, we have 3 members of our panel who will be joining me. They're going to give a brief introduction to themselves, their expertise, and their views on corrosion and its status as an important problem. The first is Mary Ryan, and she's Professor of Material Science and Nanotechnology and Vice Dean for Research in the Faculty of Engineering at Imperial College London. Over to you, Mary.
Thank you, Tony, and thank you, Derek, and the team for inviting me to join this panel. I'm looking forward to entering discussion. I guess I just wanted to maybe take a step back, and I have the privilege of going first, so won't be repeating some of these issues. But when we think about corrosion, and we've thought about this being a 3.5% GDP issue, that's a number that has not changed over it started to be measured. It's not changed over the last 30 or 40 years. So we're not getting better at this, despite the huge amount of research funding and that has gone into it, and despite the continued huge amount of money that is lost due to corrosion. When you start to dig into that corrosion challenge, there are some things that are also repeated over and over again, and that is about a third of those that lost due to corrosion is because we didn't do something when we already knew the answer. We selected the wrong material, we put it in the wrong environment, we knew there was a problem, and yet we still did it. Another third is where we actually had picked the right material and everything should have been working, but then there's some kind of excursion from the normal conditions and we weren't quite ready for that, or we extended a lifetime and that was not right. So we didn't use things operationally in the right way. But then about a third of that was not predictable because we didn't understand the systems well enough. So there's 2 pieces there's a few things that means. One is we need to do much better training and translation of knowledge into the field. We need to do much better monitoring of what's happening in the real world. But actually we do need to do a much better job of unpicking some of these mechanistic issues that underlie corrosion. And it turns out that's quite hard. And one of the reasons that it's hard is because we're talking about very complex interactions and complex interfaces, and where there's a strong interplay between electrochemical systems, the microstructure of the materials, this specific environment that material ends up being in, and quite often mechanical coupling as well. So that makes it quite difficult to study. We need to think about this across multiple length scales, from atomic up to the macro scale. We need to think about multiple time frames, from the time frame of an electron transfer reaction to the lifetime service of the material. And those are really complex scientific challenges to start to address and develop the tools that can do that in complicated real world materials and scenarios. And what that often leads to is conservatism in what we choose, right? And when we end up with conservatism in the system, we actually spend a lot more money and use a lot more resource than we needed to. That also is the reason why this is really interesting to study, right? Because some of these challenges are really hard, but really important. And there's lots of scope, I think, to do really innovative research in this space. I think the future also, we're at a critical point. I think we've all recognized this in terms of material sustainability and the energy transition. And some of those challenges, I think, bring with them some inherent corrosion related issues. So in thinking about sustainability, of course, corrosion is a key place where we lose materials, right? We're losing resource actively in the system, as well as all of those secondary impacts that we just talked about in terms of health and safety and environment. Actually, the materials themselves, how can we extend the life of materials so that we don't have to replace them more often, or we're making better use of the resource? Or how do we recycle materials better, or use recycled materials better, and understand the properties of recycled materials, right? Typically, for optimum properties, we use a pristine materials once, and then when it's recycled, it has degraded properties. How can we make some of those properties more tolerant? And at the flip side of that, of course, is some materials we'd like to disappear into the environment, right? We'd like them to be biodegradable really quickly. And so that kind of leads to this idea, which is a really interesting challenge, that you could have a programmable lifetime, right? From seconds to infinity, right? How do you think about doing that? And to do that, of course, you need to understand the material really well and the environment really well. In thinking about the energy transition, there are lots of new systems that we are now thinking about developing and deploying at huge scale that have new materials and new environments and new scenarios that are not well studied, right? And I've just told you we don't really understand what happens to metal in seawater. So now we're talking about having new alloys, complex alloys, in things like battery materials, or in supercritical CO2, or in hydrogen, high pressure hydrogen. And so there's a whole new range of, I think, research challenges in terms of understanding those interfaces, and at the same, and probably understanding new mechanisms of what's really happening in those materials. At the same time, energy transition, so there's a lot of aging infrastructure, and we have to make sure we also protect that and maintain that in a way that's safe whilst we go through the transition. So there are some opportunities, of course, in the fundamental science, but I think in terms of also thinking about deploying new technologies, there's lots of interesting opportunities, not least in data and AI and how we use that, enabled by remote sensing and the Internet of Things, and actually bringing together sensing, understanding of materials, and data analytics is going to, I think, bring us an explosion of opportunity space. There's also, and I think probably Mark will talk more about this idea of having responsive materials, and that might be a coating that can self-heal, or it might be a material that senses when there's been a challenge to its environment, so it recognizes that it's had some of these non-opportune systems. And then I think more broadly, I think recognizing that some of these corrosion challenges that we're talking about actually translate into lots of other technologies, right? When you think about to understand corrosion in an ecosystem, you fundamentally have to understand oxygen reduction and where it happens and how it happens and what controls the charge transfer and what are the side reactions. And of course, that's the key reaction you want to understand in a fuel cell. So thinking about some of these problems actually and connecting to different communities, I think gives corrosion science a real big opportunity in a lot of the new technology space. So I'm going to stop there, Tony. I probably said a lot of things that other people wanted to say, but I'm looking forward to the conversation.
No, and I think, you know, as the academic metallic corrosion expert, it was absolutely right to get you to do that first. And in the spirit of full disclosure to everyone on the call, Mary and I are related in science, but unrelated in person.
Yeah. You're my academic uncle, I believe.
and then it brings me a great pleasure to welcome our next panel member, who's Richard Jones. Richard and I have known each other and worked together for more years than I care to state. Richard's currently the Professor of Materials Physics and the Vice President for Regional Innovation and Civic Engagement at the University of Manchester. And again, in the spirit of full disclosure, we worked together with our next panel member, Mark Irwin, on an EPSRC Axo Nobel Prosperity Partnership grant that two of the organisers of this session are also involved in. So Richard, over to you.
Great. Well, thank you very much, and it's great. Thanks to the organisers for asking us along. Great to have this discussion. And so Mary talked about why corrosion is so important, but also such a hard problem to solve. And Mark, coming next, will, you know, he works for a company that makes a business of dealing with this problem by, you know, selling coatings, industrial coatings, paint for ship, paint for aircraft. and so on. And so what I want to talk a little bit about is, first of all, what the interesting science of coatings is, but also I draw from that some kind of bigger lessons about why we do research and how we and how the interaction, if you like, between applied problems such as coating problems and fundamental science, and then their impact on the wider world in terms of economics and such like. So I first started being involved in the study of paint in about in the early 1990s. So of course there's a very familiar joke that anyone who's involved in this research about, that you make a living watching paint dry. And I suppose my pitch is to say something about why, contrary to that joke, the subject's actually both very serious but also rather interesting. So I guess just as most of us, we've all probably painted something, and actually when you think about it, it's a little bit of a miracle when you take a gooey liquid and you spray it or you splash it onto a surface, and it first levels itself out into an even coating, hopefully, without holes or bumps. And of course, getting it without those holes is absolutely crucial for as a protected surface. A very typical way for a coating to fail and to lead to corrosion underneath it is you just get a hole in it. So understanding how you get that even coating, and then how it transforms into a hard coating whose function can be decorative and protective, that's really both interesting and crucial. And it's a mixture of, it's difficult because it's a mixture of physics and chemistry. So you've got the question of how you get a coating on that wets the surface. That's interesting questions of surface physics. How you get something that you can apply relatively easily, so you can apply it with a brush or you apply it with a spray, and yet it doesn't all run down to the bottom. That invokes properties we call thixotropy, the property of shear thinning. Then there's the question of, what happens next? You've got paints, they're mixtures of polymers and solvents, essentially. Sometimes it's a solution of individual polymer chains. Sometimes it's a suspension of particles. We call that a latex, because that's what natural latex that comes out of trees that makes natural rubber. It is made up of those little particles. And so you've got the question of how does the solvent evaporate, and when the solvent evaporates, how does the film form? If you are little particles, how do you come together? How do you go from a bunch of nanoscale balls to a continuous film as a result of those interfaces forming, the polymer chains wriggling together to make those interfaces? So you've got that physics, and then you've got chemistry, you've chemical reactions going on that link those small molecules together to big ones, and then you've got the chains joining together to make a network, usually quite often that's effectively an infinitely big molecule. So this all this is all the kind of physics and chemistry that underlies making a coating that then hopefully has the function that you want, that function to protect the substrate from damage, particularly from corrosion. And this is all, again, there's physics and chemistry going on here too, and it's all, not always, we don't really understand what's going on generally. You've got the physical question of how does it stop water actually going through, getting from the outside world to the material you want to protect, with a piece of steel, a piece of aluminium. And then you can include materials that chemically protect the substrate. So that's a whole bunch of properties that you need to get. So you might be thinking, well, okay, we've had paint for decades, for hundreds of years. Paint, people were making paint in the Peak District. It's actually quite a big industry around where we live in the 18th century. So the idea of putting an organic coating onto a surface is nothing new. So what is new? Well, there's a couple of things. There's new pressures on old formulations. Things that we used to use for paint just aren't acceptable anymore. The environmental pressure mean that we have to change the formulations. And I'm sure Mark will talk more about this. But we need paints that have less solvent in, so you don't get damage to that comes from the release of organic solvents. And actually quite a lot of components of paint are pretty toxic. And everybody knows about lead paint, and the fact that many of our houses were painted with white lead. But for the other things slightly less well known but equally poisonous, particularly for anti-corrosion paints, hexavalent chromium salts are very common, very excellent way of stopping corrosion in aluminium alloys, particularly important in aerospace. But what's the problem with them? They're really toxic. They're almost certainly carcinogenic. They're very bad for the skin. They're very bad for the environment. So as we've seen, in marine paints, we saw tributyl tin, again, a fantastic ingredient, really great at stopping that really important problem of stopping barnacles and other marine life growing on ships. Tributyl tin compounds, great technology, but it turns out to have really bad environmental effects. That was actually banned in 2008. So things that used to work, because their side effects were so undesirable, we're having to seek replacements. And then we got new pressures on old formulations, the need to do things differently. But then we've got new demands. And I think, we'll all agree, Mary talked about this, I think, I'm sure Mark will too. The transition to net zero, it's a massive transition of our material economy, absolutely unprecedented in the scale that's needed. And I think paints as coatings, part of the broader chemical industry, is in a sense both the problem and the solution. So what we've got to do to get to net zero is, the simple formula is that you need to electrify everything and then make all your electricity zero carbon. And that's a massive infrastructure problem for the UK. In the UK, what does that mean? It means mostly the heavy lifting will be done by offshore wind, but that will need, the new technology of floating offshore wind. So we're going to have these massive industrial constructions bobbing around in the Atlantic in the most hostile environmental conditions you can imagine. And then, in addition to that, we'll have to have some choice of new nuclear or carbon capture and storage to provide firm power. Again, huge infrastructure projects. And I think a way of thinking about this is we're essentially going to be moving from a hydrocarbon economy to a materials economy, with all this new materials that we need to create this new infrastructure. But of course, there's an issue there, because the materials themselves embody energy. Every kilogram of steel that you have, every kilogram of aluminium has had a huge amount of energy put into it. And so it's important. We've got to decarbonize their production, but we've also got to make them last longer. So, there's the one example of, floating or wind turbines going to be a really demanding environment. And so corrosion protection, protecting those things, is just one of the many ways in which the chemicals industry will need to make that transition. So I think Mark can make the case to the chemical industry. I think the case, in a sense, makes itself. It's a crucial part of the modern world, a very high value, high productivity industry, and that's going to be vital for our continued economic growth on the one hand, but making this important transition to sustainability. I just want to finish by saying something about fundamental science. And when you study an applied problem, like watching paint dry, it's important and interesting, but it also raises really new questions of fundamental science. And so in the time that I've been kind of working on these problems, really fundamental questions like how do components segregate surfaces and interfaces? How's the mobility of molecules differ when they're near surfaces, when they're near interfaces? And in 1994, we made a discovery about polymer mobility that actually arose from an old paint project, and that caused a huge amount of worldwide interest. And what's really quite nice is that we're now revisiting that question. It turns out, it's a live question. Maybe all this research since then hasn't settled it. And I think just to final, I need to mention our sponsors, Akzo Nobel, the paint company, the coatings company that supported our work, but it's been supported through a joint between AkzoNobel, the company, and the funding agency EPSRC. So it's a so-called prosperity partnership. And I think it's a great example of how, we shouldn't think of applied science and fundamental science as, fundamental being basic science being coming first, then applied science. I think the progress that you get in science is when you mix them up, you get new problems, you think about fundamental problems in new ways because of problems that these practical issues grow up. So I will stop there. Thank you very much.
Thanks, Richard. That was great, and I can see that questions are already coming up in the chat. I would encourage everyone who's here, if there are questions that have been raised by what our panelists have said in their introductions, to put them in the chat. Mark, you've been advertised 3 or 4 times now already, so it's great to have Mark Irwin with us. Mark's a researcher at AkzoNobel. He's deeply involved in the Prosperity Partnership as described, and will bring an industrial perspective to this issue of protecting the world's assets as we move into a new era of a materials economy.
Thanks, Tony, and also Richard and Mary as well. For those of you who are not aware, AkzoNobel is a Dutch multinational coatings company, and I've worked there for a little over 10 years now. It's interesting, Richard talked about the joys of watching paint dry. I've spent the first 9 years working for doing polymer development for the decorative paints division. So sort of polymers that go into things like Dulux, where because of the decorative aspect of them, a lot of time is spent actually watching in quite a surprising amount of detail how these things dry. And it turns out that it's fascinating. Richard is not wrong there. And many people have made a career out of this. Then in the last 1.5 years or so, I've been involved much more in what the company calls the marine and protective coatings area. And in that, as you've heard, I've worked with Richard and with Tony as well as part of the Suscord partnership. Within AkzoNobel, well, within the coatings industry generally, there's 2 typical purposes for coatings: decorative and protective. And how much of each of these you want depends a little bit on the surface that you're coating. So, for example, walls inside a house typically don't need the same level of protection as an oil rig, but similarly, you probably want to be able to have a very specific set of colors for your house because the aesthetic considerations are very important. Whereas for something like an oil rig, durability and the performance of the paint is far more important. It's worth mentioning as well that AkzoNobel sells into a variety of different end uses, and each has their own different corrosion challenges. So the inside and outside of food and beverage cans, aeroplanes has been mentioned already, oil rigs, road vehicles, almost any surface you can imagine on a boat or ship. All of these have their own challenges associated with them, and sometimes the challenges can start even earlier. Some static sites that can't be moved around will have to have coatings applied to them at sub-zero temperatures, and you've got to have chemistry that will work at those temperatures and still give you a robust coating in a short period of time. Additionally, for mobile assets, things like boats, they can travel to different environments. So what you then have a changing set of corrosion pathways depending on where the boat is located, the ambient temperature around, and potentially what cargo is inside it if you've got coatings which are exposed to that as well. Richard touched on the challenges associated with changing technology, or I think as he eloquently put it, new problems for old coatings, and that is very much a challenge. So the chromium-6 corrosion inhibitor, as you mentioned, works fantastically with aluminium, and that saw a lot of use on aeroplane coatings. And because of the challenges with its toxicity, that's now been phased out. And after a significant amount of research and development, a solution with similar performance has been found using lithium instead. And so we think that's where the industry is going to move in that particular regard. From my perspective, some of the challenges around corrosion come back with knowing how our coatings actually fail. And I don't just mean, yes, I can see a section on a ship which is not as it was when it came out of the boatyard new. Typically, a failure will start at a very, very small location and often will progress for some time before it's actually visible to the naked eye. And the challenge then becomes, okay, well, if you can't see where it is, how do you measure it? And by the time you can see what it is, oftentimes the source of the corrosion or the original area where corrosion started has decayed to a point where you can no longer say specifically what the cause of that corrosion starting was, or that corrosion cause was. And a separate challenge, which I guess is in some ways related, is finding ways that we can measure accurate failures that may take decades to occur when exposed to a normal environment. You know, ships may be out at sea with one coating on them for 25 years, and it's difficult to have lab tests where we can say, okay, here is a coating, we'll artificially age it in some clever way so that it's now the equivalent of 20 years old and start looking for where the defects are. It's until a time machine is invented, that's going to be a really difficult thing to do. And having accurate tests which let us say, okay, well, we know this old technology works well because boats have been using it for 50 years. That's great. But if we want to move on to something new, we need ways of showing that it is equally reliable or more reliable. The other challenges in the corrosion industry as well. And with that, I'll hand you back to Tony. Thank you.
I'm on my way. I'm on my way. One of the questions in the chat, actually, or not in the chat, I have some pre-prepared questions, and given that I'm in the Middle East, you know, there are different issues in different parts of the world. So one of the questions is you know, what are those different issues in different parts of the world in different geographic locations? It's framed as, and it's from Abdulaziz Kablan. What's the vision and strategy to combat corrosion in the Gulf states, where there is lots of infrastructure that's corroding, but perhaps for different reasons to the corrosion in the traditional marine environments? Any?
Well, I think part of it is understanding the nature of the corrosion that takes place, right? If it's something which you can take samples from and which you can then design lab tests around, yeah, you can absolutely spend your research time looking at it and saying, yeah, this is how well, I'm saying you can do this. It's not trivial, but you can say, okay, this is how in a particular environment this coating fails, and this is what we will do in order to address that. It's very easy for me to trot that out there. In practice, that can take quite a lot of effort, because a new corrosion pathway or a different corrosion pathway may be totally unaffected by tricks that work in you know, another region of the world, simply because you've got a different temperature, maybe you've got a different pH, maybe there's a different salinity that you know, sort of immersed metal or sprayed metal is exposed to. All sorts of variables exist.
Yeah, I mean, I noticed, you know, given that I am out in the Middle East at the moment, that, you know, the biggest cause of corrosion for non-metallic materials is actually sunlight, and you know, corrosion in the sense of materials degradation will be increasingly important in these areas for wind farms and solar panels. But Mary, you were eager to contribute.
I was going to make a little bit of that point, Tony, in that as we look at, especially if you look at long lifetimes, you're relying on coatings and polymeric materials to protect metallic infrastructure, then you have to think about the stability of the coating and the stability then of the subset of materials. But I was also going to talk in the Middle East, in particular in oil and gas infrastructure, you've got a very different external and internal corrosion scenarios. And internally, quite often there's a lot of H2S or CO2, so you get quite complicated and different interfacial reactions depending on the exact mix that you've got and the salinity in that pipeline. And so thinking about whether you've got sulfide-rich systems, and of course, when you deposit sulfides or have reactive sulfides in pipelines, that brings some extra catalysis actually inside, and that can then drive different types of electrochemistry. So I think it really requires this understanding of the environment inside the infrastructure, the external environment, and the interplay between if you're using a coating, the coating and the metal and the environment, and how that is evolving with time. And I think I would just come back to Mark's point. We mentioned chromate a few times, and chromate was banned, or this was brought up in the early 90s, right? We've known for some time that chromate is a terrible thing to have in coatings. It's taken us 30 years to find a replacement, and it took us that long to find a replacement was because nobody knew how it worked, right? We just knew that it was good. And actually that lack of understanding of mechanisms in any of this, I think it's going back to Richard's point, these applied challenges have got some really interesting fundamental science questions. This was one of them. How is the chromate ion enabling such efficient corrosion protection? And it was a question that was ignored because it worked. And I think we need to make sure going forward that we don't fall into that trap again, and actually then you open yourself up to a big risk of either something stopping working and you don't know why, or actually it becomes banned because you understand something new about it in the environment.
Okay, I think that discussion, that kind of Middle East discussion, plays into the question that Manasi asks in the chat, which is, Richard, you often have kind of soundbite gems, and the soundbite gem that we're moving from a hydrocarbon economy to a materials economy because we're electrifying as the energy vector needs some unpacking. So could you unpack that a little bit?
Yeah, absolutely. And I suspect I nicked the soundbite off someone else. I can't believe I actually made it up. But I think it's I think it's really helpful. So the point, hydrocarbons are a very dense carrier of energy, and they're very they're very straightforward. I mean, obviously, internal combustion engines are kind of complicated, nice pieces of engineering, but basically you're just burning things in cylinders. And so if you think about the complexity of materials in a solar cell, for example, where you have a lot of because of the kind of relatively low energy density that you're collecting with a solar cell, you actually have to use a lot of material, and that material is very sophisticated. If it's a silicon solar cell, it's enormously pure. Many different treatments and layers applied to that. Batteries likewise. Filling a tank with petrol's basically, it's basically a bucket that you put liquid in. But a battery as an energy store is a much more sophisticated thing. You've got very complex control over the nanostructure of the electrodes. Lots more to it than that. So that's really what I mean. I think that. A level both of the kind of scale of the infrastructure, the scale of the infrastructure, say for floating wind farms that we'll need to produce, many tens of gigawatts of capacity, to the complexity of the material base for things like electric vehicles. These are the things that's what I'm talking about.
Yeah, from a I read that from a chemist perspective, in that the reason that oil and gas and coal, in fact, are so good as energy sources is that their energy density is actually a lot higher than their density, because when you burn things, 2/3 of the mass of the reaction comes from the air, so they're easy to transport because you're only transporting 1/3 of the energy. The rest of the energy, the rest of the energy is in the air around you. Whereas for batteries, for example, or for in particular, you have to transport all the energy and all the storage as well. So that's a real big issue.
But I think in particularly in the battery and the fuel cell fields, there's an awful lot of learning to be taken from traditional corrosion understanding, because a lot of the limiting factors, if you look at electrolysis in hydrogen, the stability of iridium oxide, the dissolution of that is a limiting feature in expanding the hydrogen economy, and that's a very, it's not simple because we would have solved it, but it's a classic corrosion problem. If you look at battery interfaces, the lifetime and the stability of batteries are to do with those electrodes reacting in a way that's not desirable with components of the cell, right? And these are problems that we should be looking at, I think, with a corrosion eye.
Yeah. Electrochemistry, eh? It's
yeah.
Mysterious.
So just a, sorry.
I wonder then if we're moving to a situation where, certainly for generation of electricity, it's no longer about the carbon footprint of the fuel that you use, but it's more about the carbon footprint required to generate the infrastructure that generates the energy. And potentially the lifetime carbon footprint. So if you've got something which is, say, 3 times as efficient but only lasts 50% of the time of something else.
Exactly.
You've got to does that give you a net gain in energy per unit carbon?
It's exactly right, Mark. I think you've got to do a systems level calculation, right? Systems and a lifetime level calculation to understand what are the optimum ways forward.
Yeah.
Yeah, maybe there's something around the fate of materials as well. Sort of where does your material go? Can you repurpose it? We talked about using virgin materials and their recyclability. Maybe that plays into it as well.
So how do we make those system level decisions, and how do we enshrine them in policy is a real issue. The time scale over which we're going to make the energy transition has to be shorter than the time scale that we've ever made any other energy transition. And we clearly need to move away from combustion of hydrocarbons as our principal energy source. But if that brings with it a whole new range of materials choices and opportunities, we really need to avoid making mistakes in terms of technology locking for the wrong technologies that are more energy intensive and more polluting. And I see Richard's got his hand up.
That's because that's a great point, and it leads me on to make a kind of another point about the difference in the hydrocarbon economy and the net zero economy we're moving to, which is kind of in economic terms, the hydrocarbon economy is quite in a sense it's low capital, high revenue, whereas the net zero economy is capital intensive. Whether you're building giant floating wind farms or nuclear power stations, you're putting a lot of capital money up front, and then you're not really, there's not the cost of running these things is not so great. And we have some problem with that because we have a tendency to apply too high a discount rate, as the economists would say. And you haven't we're not really very good at thinking through how much do we want not to be paying a gas bill in 20 years time, and those are the calculations that we have to make, both to make the initial investments, but also to make the investments to make the things last longer. So it seems intuitively obvious that we should be spending more money to make sure that our things last twice as long, and we have done everything we can to protect corrosion, but the way our financial markets work doesn't always make that possible, and that seems not good.
And that argument works at the kind of personal level as well. The move to net zero in terms of personal transport, and electric cars are a much bigger capital investment than an internal combustion engine car. But the running costs are lower.
And Tony, a mass transport system, an effective one in a city, is a much more expensive capital investment. But that's probably what we could do.
Yeah, it's so the problem's so wicked though. Is how do we mandate it? And please, people, as we get onto these social and economic issues, if there are people who want to post things up in the chat, we can go back to material selection, but I think these social and economic issues have actually.
I think it's really interesting, and could I just maybe I could just add in that, and I think it's really important that as we think about designing these new systems, and a lot of that is, you know, designed by engineers and technologists, and materials feeds in a large amount to that. How do we make sure that we enable a just transition? You talked about a large capital person investment, right? That's a massive disincentive for large swathes of the population, even in relatively wealthy countries, to enable, right? And so how do you make sure that you have accessible technologies, right? And I think that starts with how you design them, right? And what's the impact you want that to deliver, right? And if the impact you want to deliver is profit for a company, that's the answer you will get, but you might not necessarily get the energy transition at the speed and at the level of justice that you want to have. And this comes, and we started talking about systems. It's very difficult to think about systems from just a technological perspective. You have to think about them from a political and an economic and a social perspective, and bring that in at the design level, right? So it's this kind of integrated design engineering framework, I think, for technology for the transition.
I think sometimes there's an expectation that a new technology will be a drop-in replacement for something existing, and that, well, I think it's rarely the case that you can have a substantial change while maintaining that ease of replacement. And car ownership is a great example of this. You know, the relative costs of electric cars, and indeed the infrastructure required to support them, particularly in areas where, you know, you don't have off-road parking, you don't have easy access to charging, mean that a bit of a rethink is needed on what car ownership actually means. And I've read various sort of thought experiments around the idea of having a system where cars wouldn't really be owned by any particular person. Of course you could, but it'd be financially a lot cheaper simply to have one which arrives at your house when you need it. You use it for the length of time that you need, and then it drives off somewhere else and gets its next customer. It's almost like a sort of Elon Musk mixed with Uber dream, where these things manage to very efficiently separate you from your money a little bit at a time, all the while having you know, that it's increasingly convenient, which it may well be, but for that sort of thing to take place requires an awful lot of infrastructure and an acceptance of change with that infrastructure as well, and selling that where it's not exclusively positives is difficult. You know, people are used to the idea of owning things, and I think, you know, when you buy something new as well, you feel good about it. Well, I hope you do anyway. You know, you feel like, yeah, this is going to improve my life in some way. This is something which is going to be fun to play with. Look, it's got all these new features. And if you have something which is consumer facing, which is going to last an awfully long time, there needs to be some way of, you know, let's say we've got a car which, instead of lasting, I don't know, 5 or 10 years, lasted 50 by some miracle. You know, if you've got a car that's 50 years...
by careful corrosion control and materials engineering, surely, Mark, is how it's lasting 50 years, because we've designed it that way. We've made the right material selection.
Sure, but I mean, can you
engineer
a combustion engine to last for such a length of time when you've got people like my brother driving them? I don't know.
Yeah, I think in the chat, Beverly's made the hit the nail on the head.
Yeah, and well, as Beverly, I think, you know, the idea that and, you know, I do like to kind of push the envelope with regard to policy, because clearly the short-term profit motive market will not be able to deliver the materials transition needed on its own. Right, it's going to need some nudges, some levers, and yeah, you know, Richard and I often end up having the discussion about, you know, I mean, I'm an idealistic kind of teenage communist, and, you know, my kind of pragmatic and rational friend says, yeah, that's a lovely dream, Tony, but it won't happen for this reason, that reason, and the other reason. The principal one, me being global cooperation, against vested interests. Is that an accurate reflection of our most recent discussions?
I think so.
No, I
Richard?
think it is. I think it is. Yeah. I mean, I kind of, I can say, yeah, I want to smash the neoliberal hegemony just as much as you, but in the meantime, we'll kind of try and what.
I know.
The energy systems are really.
I was going to move this back.
Well, I'll just say one thing about the energy system and then move back. I mean, the energy system in the UK is very interesting because, it was kind of, post-privatisation, there was this view that a market system would deliver everything. And, since then, there's been so many interventions, contract difference, renewable obligation certificates. The energy system is now a real gigantic mess because it's kind of, it started out with this idea that the market would sort everything. The market didn't sort everything, so it had to be nudged in all kinds of different ways. And now it's kind of conceptually a kind of real mess. And it's possibly the answer that one ought to just tear it up and start from scratch, but it's difficult to see that actually happening.
So Mary, go on then.
No, I was going to
Mary,
kind of bring
over
it back.
to you.
I was going to kind of bring it back, and I really had a question for Mark. So one of the things from the materials viewpoint is we know corrosion starts at some kind of defect, right? Often that's an atomic scale defect. Sometimes it's a micro defect. Sometimes it's a macro defect like a scratch. And we spend a lot of time. I think the mentality in corrosion and materials has been to therefore try to minimize defects in the system, rather than making systems that are defect tolerant, right? And I think if you're going to go towards a position where we have less waste, so a zero waste economy might be another way of thinking about the transition, and therefore recycling and reusing, we're going to have to be more defect tolerant. I think that in itself is a really interesting materials. And I wonder if Mark in particular has got an industrial viewpoint on where that sits in kind of the development cycle for commercial paints and commercial systems for defect tolerant coatings, I guess, but also defect coatings that work better on more defective materials.
Yeah, it's one of those challenges where the nature of defects can be quite hard to quantify because they're numerous, and as I'm sure you're aware, these things can often be very small. Okay, so yeah, you can do things like you can have adhesion promoters present in a formulation, for example. Maybe that gets you around challenging areas of substrate. You can talk about things like surface preparation techniques, which let you try and address the presence of certain defects or potentially remove certain defects. But that defect still represents an inherent weakness in a coating. And if you've got extremes of temperature or shear or pressure on a coating, that would be the point where you see failure first, because the majority of the coating is going to be able to handle that, and it'll just focus onto one point. And some areas where you will get stress cracks, for instance, at right angle joints in boats as they sort of twist in the ocean and so on, it's very difficult to engineer that out while maintaining the rest of the properties of a coating. So you want something, for instance, you could say, okay, well, we're going to lower the TG. I'll be really, a simplistic example. We're going to lower the TG of a coating. We're going to make it a little bit more rubbery, a little bit more flexible. And so that gets you something in terms of cracks where the coating is thickest and where force is focused. But the challenge is that you introduce vulnerabilities elsewhere. Suddenly your lower TG coating is less robust, say, to impact damage. And it's really a case of playing these things off against each other and finding a compromise position. And I don't think it's certainly not easy to say, okay, well, we're going to specifically target a bunch of different defect scenarios and do that in isolation while maintaining the rest of the coating properties. I think that's really where the challenge comes. And I appreciate I've used a fairly trivial example there. I hold my hands up. Some of that is born out of ignorance. I don't know the whole coating.
No, but I think it's a fair answer, right? And I think it's a challenge of co-optimization, right? In a complicated system is hard.
Absolutely, and coatings, again, as you know, are not homogeneous systems. You've got all sorts of bits and pieces in them, what the Colonel would call 11 herbs and spices, each with their own role to play, and we add them with the assumption that their interaction with each other is less than the interaction that we're hoping they give us. Otherwise, they're not much use in a coating, right? But these things very often don't work by themselves. You know, it is a complex system. And so there's a lot of levers that you can pull, but also a lot of variables that all alter, and it's all a very confounded system.
And just to come back to Manas's second question, you know, we are going to have to factor in the temperature changes and the climatic changes brought about by climate change. But actually, for the materials, those 1 and 2 degrees Kelvin, the 2 degree Kelvin that'll kill us, won't actually have that much an effect on the underlying coating. Now, in Francis's opening speech, oh, go on. Richard wants to just clear out that.
He wants to disagree with
question.
No, I think the issue isn't so much the average temperature. Clearly, you know, one designs coatings like any other material for a range of temperatures and you know, and other conditions, humidity and such like. And I think the issue is that you know, it's not so much the average that kills you, but it's the extremes. And I think, you know, it is undoubtedly the case that we're going to see more extremes of weather, and those will have an impact on coatings. And I think you know, I'm sure Mark and his colleagues are on the case already, but you know, that for you know, in buildings or in ships, your coatings probably are going to have to see more extreme temperatures, you know, not on a consistent basis, but the periods of heat wave are going to be a challenge. And yeah, so things like glass transition temperatures, chemical properties, you know, acceleration of stuff moving around, all those things will be important, absolutely.
And I think that goes back to the...
Oh, sorry, go ahead.
I was just going to say, that the kind of the first third I was talking right at the beginning, it's this excursion from optimum conditions, right? Excursions from where you've designed your material into something else will be exacerbated by these extreme events, I think. And then how do you set up your system so that you're either, you have a new system that's tolerant to that, or you have something that tells you that has happened, right? I think that there is also a sensing bit that can help us think about managing infrastructure against some of these new risks. Sorry, Mark.
So Francis and Mark, in Francis's opening speech, he talked about 3.5% of GDP per year, and Mary reflected that. And one of the things I wrote down during that opening exchange was, has corrosion been 3.5% of GDP since the Iron Age? And is it our reliance on metals that's the issue? And it comes back to, you know, Sue Natasha asked a question, given that corrosion is such a problem, should we be building plastic, less corrosion prone material? You should be using them rather than metals. And I think, you know, that's a, you know, do we have the ultimate technology lock-in with metals technology that we might help alleviate the problem by moving away from less metal intensive infrastructure?
So I think,
so I've asked you questions soon, Natasha, in a slightly different way.
Well, shall I go first? I'll try to go first. I think it's been about this level of GDP since we've been measuring it in those terms. So I don't know. I don't think anyone's done a retrospective, but probably is the answer, maybe more. You're right, and there has been over the last, I think, 20 to 30 years, a large amount of metal replacement where it could be easily replaced, right? So if you look at, you know, air fuselages, pipelines where they can be replaced. I think the challenge is getting the strength from non-metallic materials and the strength and ductility and the cost, right? And also how do you do this accelerated testing, which I think was back to Mark, how are you confident that in some of those structural applications you can use a new material, right? It's hard enough to get industry to change to a new alloy, right? Let alone an entirely new type of material. I think the airline industry and what it did, moving to composites, was remarkably fast, actually. And I think some of those lessons could be learned in replacing metals. But I think it is this challenge, the slight conservative challenge of how to swap out a material in heavy regulated industries, but also how do you get the strength performance that you need from alternative materials.
Well, I guess with aeroplanes, you make one design and then you stamp it out however many times, and also you've got some ability to measure easily measure development of problems underneath the coating, because I think it's every 5 years aeroplanes have all of their paint removed. The aluminium gets checked for defects and whatnot, and then you get your certificate of airworthiness reissued or restamped or however. It's a lot harder to do that for bridges, which often are bespoke for the area that they're in. They don't have necessarily predictable life cycles over the length of the bridge. It could be something which is designed for relatively light loads that suddenly sees itself, being used as a major bypass for a city which has grown up nearby. Suddenly there's an awful lot more load on it. Or with the extremes of climate change that we discussed about earlier, it's often not just temperature, but it's the whole weather system that comes along with changes in temperature. Is it suddenly got to stand up to winds that are twice the strength when it was originally built, that sort of thing as well. And there's a lot of unknowns there that that would be expensive to test for something that was a one-off, I guess. Likewise, I'm told you could build a boat out of stainless steel, like a mega container ship out of stainless steel. It would be possible given the grades of stainless steel we have. That the challenge is the volume of stainless steel that we have wouldn't stretch to building a mega container ship.
Yeah, you'd need a really high specification to trust that in all that chloride. But anyway.
Well, yeah,
you would. So given that that we're still in the, if not the Iron Age, the Steel Age, and we're looking to use essentially polymeric coatings to protect against corrosion, to make the assets last longer, to make sure we recover more of the embodied energy. This comes to a question asked by Michael Miller. I see lots of people who are really, really concerned about microplastics, and particularly microplastics in the ocean. And where are we in terms of balancing the environmental risk of microplastics and the economic risk of materials degradation, and how do we pay for the cleanup caused by one or other of those reactions? The question was specifically, how do we make companies pay for cleaning up the damage caused by their reactions? But I think balancing the corrosion and the coating degradation as microplastic gives us a really nice thought piece there. Which has stumped the panel.
It is. Well, the question I have, and I don't know, so I'm not a coatings person. How much? But I have worked on microplastics. How much of the microplastic comes from coating degradation? Does it wear as microplastic? How is that? Yeah. I think it's a really important question, right? To balance and this comes back to thinking about unintended consequences of one action, right? How do you measure that? So so that was a question for the people that know about coatings and whether they do result and they do degrade as microplastics. Mark's probably not allowed to say.
Well, I mean, on wind turbines, it's absolutely the case that they degrade as microplastic, because you get erosion. You literally get erosion of the turbine blade.
Yeah.
So at that point, is it acceptable to have a coating that itself degrades but at a slower rate?
Yeah.
it's going to depend on the mechanism by which it degrades, doesn't it? And I think it's part of the equation of everything else that comes off a coating. And microplastics are one thing. Tributyl tin was something that was designed to come off and then go into the environment. And in a sense, we've replaced a chemical toxin by a more physical mechanism. And then we have to think about what are the bulk of sources of microplastics. And I still, to be honest, I don't really think I got a good understanding of that. I mean, I know a big issue about, and I'm talking to a person more expert than me in this whole business about, well, what happens to all the kind of tire wear particles? We know they end up in rivers, but what happens to them? It's not totally obvious to me that they all, that's not been highlighted as being a kind of major source of microplastics in the sea. But it is my understanding that rivers generally go into the sea, I think there's been a lot of justified concern about artificial fibers in clothes. That's another major route for in that case polyester. And then one needs to think about the ultimate fate of these things. And well, Tony, the chemist, will know what happens. The ultimate fate of polyester can be different from the ultimate fate of a fragment of epoxy, which is going to again be different from the ultimate fate of a piece of polypropylene. And we know that some of some polymers are kind of pretty much immortal in terms of their chemical structure. Probably not the ones that are used particularly in coating, but that's these are questions we have to think about.
So it's now 2 minutes past 8 in Jordan, so it's 2 minutes past 6 in the UK. Our hour is up. If our panel members would want to make a closing remark, that would be really nice. And then we'll hand over to Bettina to finish this off. So, Mary, do you have any last thoughts to leave with us?
No, I mean, I think one of the things, and we were just about to start touching on this, which is around selection of materials for protection and usage, and whether there ought to be, I do think there ought to be better policies around what chemicals can be used. And, we've had some conversation around forever chemicals in the present moment. But I think this is, I guess I would just leave this with probably where I started. This is such an interesting scientific challenge to deal with, and such an globally important problem that those scientific questions will address, that I think as a community there's more we can do, but I think this is going to be a problem for a lot longer. I don't think we're going to drop down from 3.5% GDP anytime soon, unfortunately, but that ought to be our challenge, because whilst we're wasting that amount of money, that means we're wasting a lot of material and a lot of resource, right? And that in itself is not sustainable.
Well, it's 15% of the food bill, if nothing else. Mark?
For me, I think that one of the things that we've come back to again and again is that corrosion protection is about compromise to some degree. We see that you can stick a barrier in front of something that is going to corrode, but there's a challenge there in finding a coating which itself doesn't lead to problems in another dimension. Sorry, another dimension sounds a bit farcical. In another axis, So I'll give you. We talked about tires just now, and one of the criticisms of Tesla electric cars when they first came out is that they're a substantially heavier car than most internal combustion engine vehicles, and as a result, they go through tires more quickly. So they're generating more of these, as Richard commented, little balls of rubber that get scattered along the roadside. And so you're almost sort of trading one environmental consideration for another. And so some optimum has to be reached, whereby you say, okay, well, the very best we could do is this, and here is an optimal way of going forwards. And I think that it's very difficult to have a holistic view on this, because what you see as mattering most depends a little bit on where you stand, whether you're a government, whether you're an end user, whether you're a big industrial company, for example, and getting consensus on that and agreement on what is actually best will continue to be difficult, and will continue to shape where corrosion protection goes in future.
So Bettina, so over to you.
Yeah, on that note, thank you very much on behalf of myself and my PhD colleagues, Derek and Francis. So we've been organised this as part of the Festival of Debate, and it's been absolutely brilliant. Thank you so much to our panel for sharing their really, really interesting and insightful experiences and insights and expertise. I think we've covered so much from some of the current status quo, the challenges, but I think also some really interesting sort of looking ahead opportunities as to how what else might be on the horizon soon enough, by the sounds of it. And whilst we're doing the thank yous, also a big thank you to our audience for asking some very thoughtful and interesting questions. I've been monitoring the chat, and there have been some great discussions on there. And on that note, as it's now gone 6:10, we hope everyone will have a lovely evening. Thank you so much for participating and for coming tonight. And hopefully we'll get to see you at some point again in the future.
Thanks.
Thank you.